All right, this is this is problem 1.2 in Griffiths' Introduction to Quantum Mechanics, and part A. And in this problem, we are asked to find the standard deviation of the distribution in example 1.2, and that distribution we're given in example 1.2 is this. This is the distribution. Some position x, aka in this example, it's the position of rock given time t, and a rock is dropped off. Some given height h, and therefore this is the formula and the distribution function. All right. So we are trying to find the standard deviation of that distribution, and we know that the standard deviation is simply this formula, which is the square root of the expectation value of the distribution function squared minus the square of the expectation value of the distribution function. Okay? So let's first figure out what the expectation value of the distribution function squared is. Okay? So we know that the expectation value of any function is simply the integral, or the sum of a continuous function of that function times its probability density, okay, over the entire range of that function. And the range of that function is from time 0, when the rock is released, to when the rock hits the ground, and that is the square root of 2h divided by g. And I found you can calculate the total time by simply going back to the original function here, and we know that the rock will hit the bottom at a distance h. So plugging in x for h and solving for t, this will give us the total time that the rock is in the air. Hence, that is the answer for it, or this is the total time calculated. Okay, so we're finding the integral of this function over that entire time. So now we need to figure out what our probability density function is. Okay, so our probability density function. Now remember, to figure out a probability, it is simply the value of something divided by the sum of all possible values, okay? So for those of you who haven't taken statistics, this is analogous to, say, flipping a coin. You flip a coin and you want to find the probability of getting heads. Well, the probability of getting heads, so that's your one value that you're looking for, so you put heads in the numerator. And then the denominator, you sum all possible outcomes. And so this would be heads plus tails on the bottom. And then solving that is 1 divided by 1 plus 1, which is 1/2. And so the probability of flipping heads is 0.5, which makes sense. So that's what this base formula is. It's this one possible value given some time t divided by the sum, or the integral, across the entire time that the rock is in the air. Okay, and then we basically have to solve the integral on the bottom. And so you can do this at home, but I skipped quite a few steps here. But ultimately, I get this as my probability density function. Okay. Now I have my probability density function, so now we can go back to this formula. And remember, this formula is figuring out the expectation value of our distribution function squared. Okay, so we have our distribution function, that's squared, and we have our probability density function. And now we can plug those in here, and then we solve for that integral. And so I'll walk across here, but you can do this at home. I skipped quite a few steps, but ultimately I get this as my expectation value of the distribution function squared. Okay, so we're halfway done. We have this portion here to figure out our standard deviation. We have the expectation value of the distribution function squared, and now we need to figure out the square of the expectation value of the distribution function. So to do that, This is pretty straightforward because now we know what the expectation value is, and then we square that whole thing. Okay, and we know our distribution function, and we know our probability density function. And so this is a straightforward integral. And then once we solve this integral, we square that integral, and I'm almost done. And almost done. This is a recording for YouTube. And this is the square of the expectation value of our distribution function. And now we finally plug in all those values into our formula for standard deviation. And that's, again, our square root of our expectation value of our distribution function squared minus the square of the expectation value of our distribution function. And we simplify. And that's our final answer. That's our standard deviation of this distribution function. And this makes sense because all we have are h values. And it would make sense that our distribution function would, our standard deviation would depend on our height. If we have a larger h, or if we drop the rock higher up, we're going to have a larger distribution, and therefore with a larger distribution we'll have a larger standard deviation value. So as h goes up here, standard deviation goes up, and if it goes down, standard deviation goes down. So this answer makes sense.